Okay, so we're back for the second part of 522 on October 22. We introduced the idea of principal components earlier. Okay, so we talked about PCA and what it does. We want to maximize the variance on the first component. And if we select other components, we want those variances to be maximized as well, but uncorrelated to the previous components. I just want to point out something as well, is when we're talking about these constraints here, right, subject to this constraint, as I mentioned, this isn't the most exciting part, right? That's just something that we need so that the weights don't inflate without bound. But again, the most important part is this right here, right? The product of the weight times the variable. This idea is maximizing the variance, okay? Maximizing the variance of the variables and maximizing the variance of that first component, okay? So this is the component that maximizes most of the variance in the original variables. That's the idea of PCA. But remember, the constraints that we're imposing on the procedure are kind of secondary. You need to be aware of them. You need to be aware that there's constraints imposed, so you know how the weights are being selected. But you don't want to say a definition of PCA is that it's a constraint that the sum of squared weights equals to 1. I mean, that just really wouldn't make sense in describing what PCA is about. PCA is dimension reduction, maximizing the variance, but also subject to constraints. And that constraint, that the sum of squared weights equals to 1, it may seem like, wow, that's the first time we've really heard of constraints, but it isn't, because there's constraints in almost everything that we do in terms of modeling. And that's just another constraint, and it's one specific for the PCA procedure. It's one that's used in the maximization or minimization procedure in PCA. Okay, so talk a little bit about the biplot here. Just survey this quickly before we go on, because we want to close out today with introducing factor analysis and how it's different from PCA. Well, this is called a biplot, and it has the component scores of all the different cases in the data. And the cases here are made up of all these different particular states. The most interesting part of this biplot is it plots the first component against the second component here. Okay? So these are scores on the first component for South Carolina, North Carolina, etc. The most interesting part is the variables. Okay, these are the variables on components 1 and components 2. So when you look at these axes, you can match up these axes with the actual component loadings. If you look back at the table, you'll see that these are all scored on these particular axes, not on these over here, but on these in terms of the loadings right over here. So what could we say about this? Look at the first principal component, right? The first principal component, we can see that we have murder, assault, and rape. Those are relatively close to one another. Okay, those are relatively close to one another, and it's telling us the same idea as what's being told in the table. It's saying that it looks like the first principal component is made up of those 3 variables, whereas urban pop isn't really loading that highly on the first component, right? Urban pop is not loading very highly on that first component. If you spin the plot around so that you have the second component, right? It's easier to visualize if you actually like rotate this plot over so that the second component is over here. Well, then you're going to see that it's the urban pop that's dominating in terms of the size of the loading, right? So murder, assault, and rape, those all have higher loadings than the urban pop, right? So if you look at these loadings up here, you know, rape and assault and murder, they're further along than urban pop. But if you spin the plot around, you're going to see that urban pop is the one that has the bigger loading compared to these 3. So the biplot helps you kind of see in a visual sense where the variables are loading on the different components. okay, where the variables are loading on the different components. And it gives you kind of that quick view of it when you look at it. Oh, we got rape, assault, and murder. And this also means that these variables are more highly correlated with one another than the urban pop, because their vectors are closer together. Okay? So that's a look at that biplot could be useful in terms of interpreting the components. So that's what they're saying here. The blue state names represent the scores for the first two principal components. So those are the scores on those first two components. That's what those state names represent. The orange arrows indicate the first two component loading vectors with axes at the top and right, which is what we just described. For example, the loading for rape on the first component is 0.54, and its loading on the second component is 0.17. And so you can locate that value for rape as 0.54 on the first component and 0.17 or whatever it is. Yeah, 0.17 on that second component. So it gives you that bivariate location on the first two components. And you know, when you think of it, what's a biplot? It's a scatter plot, right? It's really a scatter plot, because you know, what's the difference between a biplot and a scatter plot? Well, we're plotting, you know, different things, but here we have one dimension and here we have another dimension. So if we were to, you know, characterize this in terms of a scatter plot, well, how about this is x1 and this is x2, and we're plotting those bivariate points. Okay, so that's an interesting way to think of that as well. We've just reduced the dimensionality, right? We've reduced the dimensionality into this. So in other words, we've constructed a new dimension. I don't want to call it a variable necessarily, because it's not a variable, it's a component. Because if I call it a variable, it sounds like, oh, a variable like murder, assault. Well, not necessarily, because these are observed variables that we have in our data. Where do we have this first principal component in our data? We don't, right? That first principal component does not exist in our data. It's a function of weighted assault, murder, and the other variables, but it's being constructed from the transformation, right? So, you know, we want to make sure we realize that this does not exist in our data. Does not exist. This is simply due to the transformation by eigenanalysis, in this case, of these observed variables. That's the big idea here. So, you know, we get into this idea of these unobservable variables, where this doesn't even exist. So even when we name this something, if you want to name it something, if you say, you know what, this is like, you know, crimes, well, there's no definitive proof that that variable is named crimes. You're naming it crimes based on what you've kind of surmised from the loadings in the PCA. But again, this doesn't exist in your data. So, you know, you can't even say, well, I have a first principal component and it's named this for sure. You're coming up with a name for it based on the inputs. You can liken it almost to if you have a bowl. So there's a bowl and you throw in a whole bunch of ingredients, right? So you put in one ingredient, throw in another one, throw in another one, lots of ingredients go in. And then you know, what are the ingredients? The ingredients are murder, assault, rape, and urban pop. Those are in the bowl. Then you take the big mixing spoon. So there's my big mixing spoon. I'm going to go into the bowl. And what am I going to do? I'm going to transform the information. This mixing bowl is conducting a PCA. Right? This mixing bowl is conducting the PCA. Notice that the mixing bowl isn't changing the actual data, it's just transforming it. Right? It's just transforming it. So you mix in the bowl, you transform it, and out of this, you know, out of that mixture, you pull out C1 and C2. Now there's going to be C3 and C4 as well, because we said there has to be as many components as there are variables. PCA does that. PCA does not dimension reduce for you. It produces as many dimensions as original variables. It's up to you to select the first and the second, if that's what you want to describe. because these will account for the most variance in the data. This accounts for the most, this accounts for the second most, uncorrelated to this. But the idea of the mixing bowl, to get back to that analogy, is the idea that you're not changing the information, you're transforming it. So look, when you look at C1 from here, from the mixing bowl, comes out of the mixing bowl, you ask yourself, hey, what is C1? All right, what is C1 made up of? Well, it's kind of circular, right? What's the only thing it can be made up of? The ingredients that went into the bowl. There's one ingredient, there's another one, there's another one. You threw them all in. So now you're going to say what C1 is made up of, those ingredients. Does that sound a little bit circular? Yep. It's kind of circular, right? That's why at the beginning I said, make sure you got the bowl right. Because if you got the bowl wrong, your components analysis is only as good as what you're putting into the bowl. The components analysis or any other statistical procedure cannot do something to your data that's not already present in your data. So you definitely don't want to think that, it'd be a huge mistake to think that components analysis is like discovering things in your data that are not there. And like, you don't want to think of it as like some kind of a mystical technique that's unearthing the truth or something like that. No, it's only as good as what you put in there. And that's true of any statistical procedure, but especially when we look at these dimension reduction techniques, it's really, really important to emphasize that that component structure is going to be a function of the ingredients. So if I take, rape, assault, murder, urban pop, and I decide I'm going to add an X5, I don't know what burglaries or something like that, or city dwelling status or something, I don't know, some other variable that I put in. Well, that's like putting in a new ingredient to the bowl. So my component structure might come out to be a little bit different. So, and just to reiterate on that, it may seem kind of circular because you only get out what you put in. You're just transforming information. Really important. Now, I've spent like the last 5 minutes talking about that. It seems like 5 minutes because that's going to be really, really important when we start talking about factor analysis. It's important in PCA, but it's going to be even more important in factor analysis. And we're going to have to work on the language of how we talk about these things. Because if you say you're discovering components and you're discovering factors, it's more of a transformation than anything else. It's not a true discovery of anything. And I'll talk about that further in a minute. So there we go. This indicates that the crime-related variables are correlated, tend to have high murder rates, etc. And there's another interpretation of principal components. You could read that over if you like. We're just going to skip over that. Talk about the scaling of variables. Okay, the scaling of variables actually is very, very important. So we want to kind of heed this idea here that the results obtained when we perform PCA will depend on whether the variables have been individually scaled, such as producing z-scores. Okay. So the classic case is you have the raw data and you have the scaled data, like standardized data. Does it matter that we scale the variables? Yes, it does. Look, it's really, really illustrative demonstration of how it can really, really matter. So here we have the unscaled. Let's start with the scaled. We have the scaled over here. This is the components analysis we just looked at. It's the same biplot. Well, look at what's happening in this plot. We just looked at it, right? We have rape, assault, and murder, and urban pop. If we were to unscale the data, so if we hadn't scaled the data, now look what happens over here. So again, let's kind of draw our conclusion on this one. What did we say? We said, well, on the first principal component, murder goes out here, assault and rape. So these three are dominating on the first principal component. And that was true by looking at the loadings as well, right? These are loadings. These represent loadings. But if you look at the table of loadings as we did, you'll see that that's the case, right? That was true. That was true. That first principal component seemed to be made up of mostly murder, assault, and rape. Urban pop, not so much, because look, it's got much lower loading up here. Right. So is mostly those three variables. Now look how it can change if we did not scale the data. So if we unscale the data, okay, look at how things change. Wow, it almost looks like it's a different analysis. Yet it's on the same data. It's just that it hasn't been scaled. So what are the consequences of this? Well, we had our interpretation here pretty much down pat. We kind of saw what was going on with the data. In this case, well, let's interpret it. Assault is up here on the first principal component, right? Assault is up here on the first component. Here, assault was here, and it was pretty close to rape and murder. In other words, these had similarly large loadings, right? They had similarly large loadings. Here, assault is dominating, right? Assault is dominating. Now, assault is dominating. Notice that we are in raw scores here. It's unscaled, whereas here, it was scaled. So how do you interpret this? You interpret saying assault is dominating on the first principal component. How's murder doing? Not so much. Look, murder is only over here. Rape is only over here, right? Urban pop, sorry, I should be looking at this axis here, right? They're very, very close to 0 over here. This axis is for the component scores. We're looking at the actual variables, so we're looking at the loadings over here. But we see that assault is dominating. Now the question is, why is assault dominating? Why is assault the dominant variable in this particular analysis on the first principal component? This has to do with what principal components is actually doing. So what did we say principal components was doing? It's transforming the information in the original variables onto new components. Well, how did we define the information of the variables? We defined the information, remember earlier in the chapter when the author said, it transforms the information. Well, what is information, right? You got to ask those questions, right? You think, well, what's the information? Well, the information are the variances. The information are the variances for 1, 2, 3, and 4. That's the information that's actually being transformed. You're transforming the original variances onto new dimensions. So you can kind of see what's happening with the unscaled is that the assault is dominating, but it's not dominating necessarily because it's, boy, that's like so central of a variable, right? When you first look at these things, my goodness, assault, there must be something special about assault here. Well, not if you scale the data. If you scale the data, assault is in line with rape and murder. But in this particular analysis, it's far off. So what's going on? Right? Ask yourself, like, what's going on with this? Why is assault dominating here and not here? And the only answer could be, well, looking back as to what PCA does, which is maximizing the variance of the variables. So what it's doing is it's saying assault has a high variance to begin with, right? Assault has a high variance to begin with. Therefore, when you do the PCA on the unscaled data, this variable is dominating, not because it's that dominant of a variable, because look, when you scale it, it's really not that dominant. I mean, it's up there, but it's up there with rape and murder. Here it stands on its own, not because it's necessarily most important, but because it has a lot more variance than the other variables. The assault has a lot more raw score variance than the other variables, therefore that's why it's dominating. Now you look at that and say, my goodness, like principal components is like the most horrible procedure ever for it doing something like this. How dare principal components do this? What a bad technique. If it's like saying this is most important in this plot simply because it has the highest variance. And the answer to that is it's doing what it's supposed to be doing. Principal components is doing exactly what it's supposed to be doing. It's not a horrible technique. It's maximizing the variance of that component. And it just so happens that this particular ingredient in the bowl, different bowl, okay? This particular ingredient in the bowl, there it is, a salt has a high variance. So in other words, it's contributing a lot to the solution, right? Rape is over here, murder over here, urban pop over here, but assault is dominating here. Therefore, it makes sense from a principal components analysis point of view that when you extract components from this, assault should be dominating. Right? Assault should be dominating because it's contributing more. Right? It's contributing more. I forget if assault was 3 or 4. I think it was 3, or maybe it was 2. But it's contributing more information. So this makes perfect sense. So you don't want to think that the unscaled analysis is like some kind of like faulty analysis. That's not the point. You don't want to say, well, unscaled is like the wrong analysis. It's not the wrong analysis. It's just looking at things as from a different perspective from the scaled. And it's not a simple transposition of one analysis to another. That's the point. But I want to emphasize that don't pick on components analysis for doing something like this, because this is exactly what it should be doing. So this analysis is not wrong. This analysis is not wrong. This analysis is not wrong. Neither one is right or wrong. It depends on what you want to look at in the data. And if this variance domination is important, and you want that to be reflected in your solution more because of it's a bigger ingredient, then looking at this analysis could make a lot of sense because it has that higher variance to begin with. However, in most cases, the authors will suggest scaling it. Okay, so on the left, the variables scaled have unit standard deviations over there. So each one of these starts off with the standard deviation of 1. That's what the unit is. Okay, starts off with the standard deviation of 1. So what are we doing with our bowl? We're saying before you put in the ingredients, scale them. Each one going in with the standard deviation of 1 before they go into the bowl. Therefore, a salt doesn't have that dominating effect. You can see the effect for the second principal component too is urban pop up here. Urban pop is dominating on the second component, right? It's got like a huge loading over here, whereas these are all close to 0. Over here is dominating too. So, you know, it's kind of similar in terms of the effect that urban pop is having, but it's the assault one that really kind of stood out here. But again, want to emphasize, one analysis is not wrong, one analysis is not right. PCA is doing what it's supposed to be doing. You have to be knowledgeable of what you're inputting into the computer, into the PCA, in order to draw an appropriate conclusion. As a general recommendation, doing the scaled and unscaled is a good idea, so you can compare the two. But you can also see, right, you can also see how somebody can not mislead, but maybe misrepresent the data. Or if you're not familiar with what PCA is doing, then you could easily, like if I flash this data to you in a matter of 10 seconds at a conference, and I go, I did a PCA on the analysis, look at how important assault is. Look, wow, look at assault is important. I show you this, and I show up the slide for 10 seconds. You leave with the impression that assault is, wow, that's a dominant variable on the first principal component. When really what's going on is it just has a high variance. And that's why it's always important to know what's going into the statistical procedure so you can draw an appropriate conclusion. So this is what they're saying down here is assault has by far the largest loading on the first principal component because it has the highest variance among the 4 variables. Scaling the variables as standard deviation of 1 is recommended. But again, doesn't mean that the unscaled is wrong. PCA is doing what it's supposed to be doing. So they say it here again, right? So it's good to scale your data. And in your lab that you'll have to do, going into the final exam, you'll have to look at scaled versions and unscaled versions, and you can compare them. And again, if we were doing this research for real, this would be studied a lot, right? You don't just want to run the components analysis and just like write it up in period. You want to be looking at stuff like this, right? You want to be looking, say, interesting. Which one should we report, and Y and stuff like that. So we've spent some time on this. You should also spend some time on your components analysis or any other statistical procedure do. You always want to look at it very carefully. Okay, so uniqueness of the components. They are unique. However, you will see, because of the way they're constructed with vectors and things like that, you will sometimes see from software program, a flipping of the sign, but it doesn't have the effect on the principal components analysis. So sometimes you run it in R, then you run it in SPSS or Stata or SAS or what have you, and you'll see that the signs actually flip. What was negative in one is now positive, but the actual principal components analysis is still operating. You'll just see a flip in sign, and that's because of the way these vectors work. So the principal component loading is unique. We say up to a flip in sign, up to a sign flip, but it's unique. The fact that you're getting different signs or opposite signs doesn't necessarily mean you're getting a different components analysis. It's still a unique vector. Proportion of variance explained. This idea is not new because we've talked about it, that you looked at your components analysis like C1, C2, C3, and C4. Well, it's reasonable to think that if you want to know how much variance this accounts for, you should be able to get a number called the proportion of variance explained. Okay, why we have to abbreviate this, I'm not quite sure. Why don't we just say proportion of variance explained? Nonetheless, you know, how about we throw in another abbreviation so it becomes even more confusing, right? So now you have to memorize like PVE. What does PVE stand for? Just call it the proportion of variance explained, right? Too much abbreviating in words sometimes. It makes it unduly difficult, right? It's hard enough to get the technical details. We don't need more abbreviations. Okay, so I digress. That's a side note. So you look at this and you say, well, these here have to sum up to the total variance in the variables, right? It has to sum up to the total variance in the variables. So you have component 1, component 2, component 3, component 4. So if you want to get a sense of the importance, and I use the importance in quotes, okay? I put big quotes around the importance. You can take this as a ratio of that total variance, because this will sum a total, and you can go C1 over the sum of those components in terms of variance explained. So the total variance present in the data is defined as that total variance. But when you conduct the components analysis, you're going to look at that proportion of variance explained. And these are called scree plots. And scree plots are nothing fancy. Scree plots actually historically were most useful when computers weren't around. And you know, people spent like a long time doing their factor analysis and components analysis, because computing all this takes a lot of time. So you'd imagine like years ago, doing components analysis was a big job. Now it takes a millisecond. But plotting this out was very useful for researchers because they could see a graph of the proportion of variance explained. Now you can get the eigenvalues really, really quickly, and you can measure proportion of variance explained. You don't necessarily have to graph it. The way you would look at this, though, is you look at the proportion of variance explained here, here, here for the different components. And what you're usually going to see is you're going to see like a drop here. Okay. You know, this one here, sometimes we say, well, look for the bend in the elbow. I mean, here, I don't really see a bend in the elbow, but I would look at this, I'd say, looks like component 1 is accounting for most of the variance. And these two, well, maybe not quite as much. So maybe this is the one I keep, or maybe I keep 2, depending on the loading structure, right? When I look at the loading structure, I may decide on 2. When I look at the scree plot, I may decide on 1. That's a subjective decision. But the scree plot will give you that proportion of variance explained. Portion of variance explained has to sum to 1. It has to sum to 1 for the reasons that we've talked about. If you're looking at the proportion, well, it's a portion of the total, so it's got to sum to 1. If ever that doesn't sum to 1, well, there's a problem, or all of your components are not being represented. There's the cumulative proportion of variance explained. So there you're getting it up to 1 over here, as we said. Why might this be useful? Well, because then I can say, you know, if I, take the 2 component, well, it's cumulative is whatever, about 84 or whatever proportion that is. You're not going to be interpreting 2.5 components because there's 4 components. So be wary of how your axes turn out. You don't want to be like looking at an axis and just because the computer plotted it that way, looking at 3.5 and all of a sudden believing there's 3.5 components in your data. So beware of axes. So that's what this is describing here. So we have the PVE, proportion of variance explained, of the nth principal component is for that given component over the sum of those x squared values. So this is how you can compute the proportion of variance explained. And those are the cumulative that we just talked about. So with our USA arrest data, we see that 62% of the variance in the data is in the first component, and the next one is 24. So I was pretty close with the 87. I think I said 84, but that's about 87%. And we talked about the scree plot. So that's how you're looking at that. Again, the idea is the dimension reduction, right? So, you know, imagine if you can say, I've taken 4 variables and I've reduced the dimensionality down to 1 component, and it accounts for 62% of the variance in the data. Okay. I like to say the variance in the variables is a little bit more in line with what PCA is doing, but saying variance in the data is okay too. But the point is, it's showing 62%. So what's the pragmatic utility of that? Going, instead of having those 4 variables, I've reduced the dimensionality down to 1 dimension that accounts for 62%. If I take 2 dimensions, I've got 87%. Now, without knowing those loadings, if I were to, you know, do this blindly, or, you know, like almost like an alien were to do it without knowing what the variables are, that's kind of a nice thing, right? 87%. Give me 4 variables. I can explain 87% of the variance, right? Because that's what you're explaining with the first 2 components. That's pretty interesting. That's, you know, that's pretty good, right? Because that almost accounts for like 100% of what those 4 variables are giving you. So you take 2 components out of the mixing bowl and you say this accounts for 87% of what went into the mixing bowl. Dimension reduction. Now with 4 variables, it's not terribly interesting, but you can imagine if you have 1,000 variables. Imagine if you have 1,000 variables and you can explain 62%. Well, let's go with the 87%. You can explain 87% of the variance in 1,000 variables based on 2 components. Right? That would be like really interesting. Now you say, well, so what's the point, right? What's the point of doing that? Well, the point of doing that, not only for dimension reduction purposes, because maybe we just want to reduce the dimensionality to find out kind of like what's in our data in that sense, right? What's going on in our data? Let's kind of see if some of this stuff goes together. Well, you might want to actually use that information in another analysis. So you can get component scores, and instead of using x1 through xn, let's say these are 1,000 variables, you're never going to run a regression with 1,000 variables, right? You're never going to take those 1,000 variables and make them predict y. So in such a case, doing the PCA might be of value in a dimension reduction fashion so that you're reducing this down to, say, 2 variables, 2 components, the 2 components. And then saying, instead of doing this analysis, I'm going to do y as a function of C1 and C2, where these are component scores. Again, the reason, does that make sense? I hope that makes sense, that you have 1,000 here, and you've reduced the dimensionality down to C1 and C2. It accounts for 87% in this case. So you're losing information, but you're getting most of it. So imagine if these are like COVID-19 symptoms, and you know, imagine if we had like, well, it's an unrealistic example, but let's say we had 1,000 different symptoms. And saying, you know, instead of predicting COVID outcome, right? This is COVID outcome of some kind, COVID out. Instead of having 1,000 different symptoms, let's see if there's some underlying dimensionality to that, such that we can reduce it down to 2 composites, two components, and then let's use these two components to predict COVID outcome. That would be a correct use of using components analysis. And like I say, you may want to even name the components. You may want to name the first component, looks like that has to do with mostly feverish symptoms or something like that, or what have you. And the next one is mostly like a physical symptom or something else. And that would be a correct use of it. Now, I'm talking about this use of it in terms of substantive theory and predicting COVID outcome, but also you can use PCA blindly as well. Like that's sometimes used. And let me give you an example. Maybe there's a whole bunch of things that predict stock market returns, right? If you think about the person on Wall Street, they're trying to see what happens to their stock over time. So there's the oil crash, and then it comes up over here like this. They're trying to predict what's going to happen. Well, maybe they surmise that they have like 500 different variables that they subject to the components analysis, and they want to be able to use them in an additional analysis to predict stock market returns. Well, they may not care about the theoretical implications of those variables. They just want to maximize that predictive ability. So the reduction of components into C1 and C2, let's say, could be entirely atheoretical so long as it gets the job done and it maximizes prediction on the outcome. And that is, sometimes used for those purposes. It's very atheoretical, but the user doesn't care because they're just going to say, well, does it maximize the return? And if it does, I don't care what those variables are. I don't care what the components are even constructed of. I just care that it does this. And if it does that, well, then it's okay. Now, if you're looking at it from like psychological theory or scientific theory, you're usually not going to use PCA in such a blind manner because you're going to want to look at what are those variables that are in the mixing bowl. Because theoretically, you want them to make sense too. Otherwise, you're not going to be able to explain what's going on, right? As a scientist, you want to be able to explain phenomena. You're not interested in simply just maximizing a prediction. You want to explain why the prediction works. Or at minimum, you want to do some cross-validation and try to build a theory, right? So from a scientific point of view, you're also doing this theory building. Example, let's say that you're trying to, as a researcher is trying to maximize that COVID outcome idea. That's a theoretical situation. So let's say they take those 1,000 variables, and one of the variables ends up being, like hair color. Okay, so one of the variables of those thousands is hair color. Well, from a theoretical point of view, you want to be able to explain why hair color is having some kind of effect on COVID outcome. It's not enough to just predict COVID outcome. You want to say, is there something to do with hair color? Does that suggest a different gene across hair colors? Is that a correlate, spurious variable, right? Is it a correlate to something else that's actually accounting for the COVID outcome? It becomes really important to build the theory around those variables and not just blind prediction as in the stock market case, as an example. Okay. So how many components to use? Well, we've talked about all this. The visual analysis is after the fact. Okay. Unfortunately, there's no well-accepted objective way to decide how many components are enough. That has to be made subjectively, almost like on a cost-benefit ratio of how much information are you willing to lose, and how many components do you want to keep? There's no right answer. It depends on what you're doing. So that's why I say you can run the components analysis, it takes a millisecond. The decisions after and how you're going to use the components in your research and how you're going to interpret them becomes something that's dominated by the scientific application. That's why also if you do a stats analysis for a researcher and the researcher, you jointly determine that a components analysis is a good idea, you are going to be continuously talking to that researcher to find out how many components they want to keep. If the researcher, if you're working in your lab and the researcher asks you, how many components should I keep? Usually the answer is how many components do you want to keep? It has to go back to the researcher. And that's why research overlaps with stats, a great deal. Is oftentimes you cannot interpret the statistics unless you understand something about the research domain. There's no definitive cutoff by how many components to keep. It doesn't work that way. It has to be merged with research considerations. Variable importance has to be merged with research considerations. What method you use to select the correct model has to be merged with research considerations. It always has to be in the context of what you're doing. Okay, so something to keep in mind as well. So we say it's subjective, right? It's subjective. But I will say it's subjective, and again, subjective doesn't mean like reckless. It doesn't mean, pick how many components you want. It doesn't really matter. It's subjective. It means that good researchers are familiar with their research area, right? They know the history of their research domain. They know what's been found before. They are keeping in touch with people doing similar experiments. They know the literature. So they're in a position to make some good decisions there. So subjective does not mean naive. It just means that you have to look at that researcher judgment. And here's what we were talking about just earlier. This is the same thing as we talked about, 3 stars, because remember the last time when we stopped talking about Ridge and the lasso, we stopped at principal components analysis. And I said, well, we're going to survey principal components analysis, and then we're going to see how it can be used in that procedure. Well, this is one example of how it can be used. And this is really, really interesting because the authors here say that it could be used as a tuning parameter to be selected via cross-validation. Okay, this is like a really, really nice idea of how, doesn't mean you're going to do this all the time, and you may rarely or ever do it. But remember, we talked about the tuning parameter lambda equivalent to S, depending on the formalization of the ridge or the lasso we consider. Well, now we have potentially another tuning parameter. So if you want to say minimize MSE, mean square error, in terms of your regression prediction, the number of components may actually be considered to be a tuning parameter. Now that brings us away from the subjective, right? That's not subjective. That's based on minimizing MSE, which we were doing all along in our previous chapter that we looked at. So you might want to say, well, which one, number of selection of components, is going to minimize MSE in the cross-validation techniques that we looked at. So which one has the lowest cross-validation error for 1 component, 2 component, 3 component, 4? Keeping in mind that as you increase the information, well, you're going to do the same thing as you do in any regression. You're going to increase your R squared, but you can look at how much more does it contribute in terms of that minimizing the cross-validation error. And that could either help make your decision, or it could make it for you entirely if it's atheoretical. So that's what we were talking about last time. So that whole section in the previous chapter where they start talking about principal components analysis, we had to get to this chapter to understand what PCA actually is. They talk about it in the previous chapter, but they don't unpack it like they did here. So now that we know what principal components analysis is here, you can go back to the other chapter and look at that, and you see what they're actually doing. They're using the components in the regression analysis in terms of helping to select the correct model. Okay. So that's what that's about in terms of PCA. There's other uses of components analysis. And I mean, components analysis is a book length topic. There's like 300, 400, 500 page books written that are called principal components. That's the title of the book. So it's a huge topic. But you have the idea now of when you might want to use it, what it does, and it's the idea of a transformation. Transformation and dimension reduction. So next up, factor analysis. I'm going to intro that in some space right here just to get us where we need to be and to compare it directly to components analysis, the main difference between factor analysis and components analysis. Well, in PCA, we computed a component, right? This was going to be a component, is a function of AX plus AX plus AX, etc., right? So these are our scalars, our weights. That's what the loadings were the A's. The X's were what? What were the X's? These were observed. Now, why am I using the word observed variables? I mean, it sounds kind of strange, right? We have X. Well, X is observed. Okay, it's observed. Hopefully it's correctly measured as well, right? Remember, if you're putting into that bowl, there's the bowl. If you're putting into there X1, X2, and X3, the components analysis is reformulating that variance. But boy, if these variables are poorly measured, then really, then what does C1, C2, C3 mean? Not very much, because these don't even mean very much, right? It's kind of like extracting a dimension reduction from stuff that is poorly measured in the first place. And if you, it's kind of like if you look at the polling for the election, it's not quite the same as this, but you can think of it, right? They get the poll results and nobody knows what to think of the poll results anymore, right? So you got like 45 to 55, Biden, Trump, or whatever, and nobody knows what this means. But then you say, well, we'll get rid of the error in the poll and say, you know, is this within the margin of error? That's not the question. It's not the question of the margin of error between the two results. That's a question in the polling right now, as it was in 2016. What's the real question? Are we even measuring what we want to measure? Because in 2016, they weren't measuring what they wanted to measure because I think a lot of people were underreporting the Trump vote. So you see, it's the same idea here, is what you measure. You know, not only is the candidate predictor problem important, but it's what you're actually measuring and whether you're measuring it properly and what these X1 and X2 and X3 actually represent. That's the most important thing. So, you know, what I like to say is before you do a components analysis and make it predict other variables and all that, maybe this should be, you know, the dissertation. Are we measuring self-esteem correctly? Is the BDI survey of those items actually assessing something called depression? And, you know, and you can open up the critique on that and reevaluate that as to whether those items are actually measuring something called depression before you subject them to a stats analysis. Because, you know, the old adage is garbage in, garbage out. Now, that doesn't mean these are garbage, but it does mean that you can be critical on whether you're actually assessing those. And what I encourage people to do is do a thesis on measurement, right? Examine the measurement of it. And that's the biggest problem in psychology, is the measurement of variables. It's not the stats analysis. The stats analysis are fine. It's the actual measurement. And it's even a problem in the polling, as we're seeing lately. So, you know, and you look at the polling and you say, well, you got the difference of 55 to 45. Well, when you call somebody, say, who are you voting for, Biden, Trump? What are you getting? You may not be getting the accurate measurement. You may be getting somebody lying, misleading, or something like that. The other issue when we think of the election is the base matters. Now, I'm not talking about the political base here. I'm talking about the base that turns out at the election. You know, so this could be 55 versus 45 for Biden versus Trump. But if nobody's showing up on election day for Biden, people don't go out to vote, but a lot of people show up for Trump, well, then this doesn't really matter as much anymore, right? Or it's, even if these figures are true, even if these figures end up being true, if everybody who goes out, you know, votes for, you know, here's the actual number of people out on election day for Trump versus Biden, well, then Trump wins, even if the sampling had 55 versus 45. So not only do you have the measurement issue, you have the expected turnout. And that's why in the polling, when they talk about the models, they say, you know, it's just like the COVID. What do we hear Dr. Birx and Dr. Fauci say for the last 6 months? They say, you know, when they present a new model, what do they say? They say, well, models are based on assumptions, right? That's the first thing they said. You could tell they're like such good scientists from the first day when somebody asked the question, what do you think of that model? And the first thing they say is, Well, models are based on assumptions. And it's like, wow, bravo, because they know that's what I'm like, I keep telling you guys is before you look at any model, go, whoa, this is based on a whole bunch of inputs that are not determined by the data. They're based on assumptions. And that's the same thing with COVID. It's the same thing with the polling, because then they have to make an assumption or an expectation or an estimate of how many people are going to turn out. If they assume equal turnout for Trump versus Biden, well, that could be completely wrong if it turns out to be different on election day. So the 45 versus 55, it's not just a matter of computing a confidence interval for the difference. It's the measurement, it's the assumptions that went into the analysis. So speaking about assumptions, what's factor analysis about? Well, there's our PCA. There's our component is equal to observed. And we started talking about those variables. Those are observed variables. Now, why do we call them observed? Well, they're presumably measurable variables that you can get information on, right? You can get information on those variables. Notice that in the principal components analysis, these weights apply to observed variables. We're assuming that you can get a verbal score, an analytical score, and a quantitative score, to use another example, right? We're assuming that you can get a measurement on that. Again, psychometrics course, theory of measurement. Are you assessing verbal ability? Entirely different question. We're assuming you can for the purpose of this. We're assuming that you can get those things. So again, once we assume that, now we'll move on. You're weighting the different observed variables. What you're producing is a linear combination of observed variables, right? The linear combination is observed variables. Factor analysis doesn't do that. Okay, factor analysis doesn't do that. What factor analysis does is it takes X, and this is coming right from Mayer on page 24, the model in Mayer of page 24, X is equal to now this is a slightly different symbol. X is observed, right? These were the observed variables here in the PCA. The factor analysis model hypothesizes that X is a function of unobserved variables with particular weights. So these here are unobserved. Sorry, that's not very good, is it? Boy, that really didn't work out. Let me try again. Unobserved. Okay, these are unobserved. So the factor analysis model is saying observed variables are a function of unobserved variables, weighted similar to these weights here in concept. Okay, these are going to be similar ideas. There's going to be weights applied to the unobserved variables. So let me just be a little bit more forceful in the writing here. Writing too light over here. So these are observed, unobserved, and then you're going to have an error term. And these are going to be loadings. So the crucial difference between the PCA is that you're now modeling the observed as a function of unobserved. In here, there was no unobserved variables. Right? There was no unobserved. These were assumed to be observed. The X1, X2, X3 were assumed to be observed. If anything, if you wanted to say you're producing an unobserved variable, even though we didn't really call the component unobserved, we just said it was reducing the dimensionality. But if you really wanted to, you can kind of say, you know, that Y is not being directly observed. Therefore, it's unobserved. So when you plotted those components and we put C1 over here, if you wanted to, you can say, it's kind of like unobserved, right? It's a transformation of the data, but we don't see it directly. That's why I said earlier, I said that component 1 does not exist in your data. So in that sense, it's unobserved. Even though in PCA, we usually wouldn't talk about it like that. We would just say this is the dimension that's generated. But you can liken those things, and that would be okay for understanding how it relates to this. Here, the observed is written as a function of unobserved. So let me just conclude this with the analogy that's going to really, really help for this, because the idea of unobserved is this. There's the water. Up here, you have verbal, quantitative, and analytical. You observe these variables on people. You measure their verbal, you measure their quantitative, you measure their analytical. This is what factor analysis does. Factor analysis hypothesizes that underneath the waters, okay, and this is kind of like a metaphor and analogy. We'll talk about next week. What it really does is simply like fits a model, but the idea of factor analysis is that there's some kind of a latent structure. Okay, this is latent. Here comes the idea of the latent variables that we've been prepping for. This latent structure gives rise to the relations among these variables. Okay, so it gives rise to the relation. So underneath these observed variables is a latent structure that's responsible in that sense. I mean, you don't even know what word to use after a while, because it's like, it's not responsible. It's just, there's something that's kind of like giving rise to these observed variables. And in this particular case, as a simple example, and I'm kind of making it up, that I'm calling intelligence by verbal, quantitative, and analytical, we would say, you know what? I've observed you on verbal, I've observed you on quantitative, and I've observed you on analytical. What could be possibly giving rise to these characteristics you have? And we might theorize that there's something unobservable called IQ. There's something unobservable called IQ. In other words, if we return back to our function statement or our model equation, the observed is a function of the unobserved. The observed is a function of the unobserved. The observed is a function of the unobserved. It's the unobserved variable that's responsible, or the true thing that's generating this. That is what factor analysis is, and the main motivation for factor analysis. That's different from components analysis. Components analysis, it's not like that. These are the observed variables. Factor analysis, we want to explain this by this. Okay. So it's the unobserved giving rise to the observed. Here, there really is no unobserved, and our linear combination is on observed variables. Whereas if you were to liken this directly as the quickest comparison, and it's not perfect, but the quickest comparison is this. Watch, y is equal to ax unobserved. That is going to be a factor, whereas here it was observed. Okay, it gives rise to the observed variables. So there's our first look at factor analysis. We'll finish that off because after we get past these very, very important distinctions, we'll be able to roll faster with it. And we'll have to bring in the MARE notes a little bit more. But I'm on page 24 of the MARE. I've identified the model in 2.3. And next week, we're going to talk about the things that MARE talks about very briefly. We're going to expand on it because there's a lot of problems when we generate a model like this. And we're going to talk about all those problems and what factor analysis actually does on a technical level, so that you know that when you see factor analyses, you know what can be concluded from it and what cannot be concluded. So next week will be very, very important, because factor analysis is used a lot, especially in psychology, and it's important that we understand its limitations. Okay, so that's it for this week. We will see you next time.